Hello and welcome to the character movement component tutorial. We're going to be running through some very fun stuff and trying to figure out how this behemoth of a class works under the hood, how you can create the same kind of movement abilities and movement code you'd find in other games that you quite like, or perhaps your own, custom code you want to create for your particular project. Basically, if you want to create something in multiplayer, or just, in general, when it comes to movement in Unreal Engine, the UCharacterMovementComponent component is your one-stop shop. Running up and down ramps, jumping onto moving platforms, and moving with that platform with no input. So much tech is under the hood here in this component for you to just look into, expand upon, and use in your games, like I say, whether it's been single player or multiplayer. But of course, setting this whole thing up to work properly in multiplayer is quite a challenge. Probably more of a challenge than it should be. But we're going to run through all of that, show you how to do it with a comprehensive C++ solution, as well as a pretty cool new plugin that allows you to do a bunch of this stuff entirely in Blueprints. I'm also going to be showing you some pretty cool little extra things you can do and just sort of hack the component to make things easier to add. Basically, if you are not someone who enjoys diving into C++, or if you're working with a team that wants to use an entirely blueprint-based solution, well, that kind of approach might work better, and we'll run through all of it. So without further ado, here we are in a brand spanking new C++ third-person template project. This is included with the engine, and you'll be able to, basically you can build on this, or you could look into something like the far more comprehensive and complex Lyra from Epic Games, which has an entire multiplayer shooter setup with all the new tech running behind it, all the new animation tools, all of the new gameplay ability stuff. But we're not going to be covering Lyra today. But if you are looking for a great jumping off point that might blow your mind a little bit, look at Lyra. That's basically a really good example of how a full project might come together with multiple divisions working together. But in this tutorial, as mentioned, we're not going to be covering Lyra and all that kind of stuff, or we're not going to be covering gameplay abilities just yet. There might be a future episode where we cover a gameplay ability system integration that works with the character movement component. But one important little thing to note there is that those two systems are two entirely different beasts, two behemoths, and to get those two things to work and talk together is a bit more work, but we might cover that, as mentioned, later on. But for now, we're focused entirely on the character movement component. Oh, before we get started, obviously, when creating this tutorial, I scoured the internet for various resources to sort of assist with the creation of it, as well as offer you more value. And I found quite a few things. I actually found another excellent, brilliant character movement component tutorial from a developer by the name of Delgoodie. And I'd actually highly recommend checking out this entire playlist, this course over here that he has here. You can see a little introduction, and then an architecture overview, and then a whole C++ integration of multiple movement modes. We're talking about sliding, wall running, all that good stuff. I also actually asked his permission to showcase the wall running implementation in C++ in this tutorial, and he said, "Nah, go for it." Really, really nice guy. He also pointed me in the direction of another document that he put together that covers the packed movement stuff we'll be covering in the multiplayer section of this tutorial. Super useful information, a whole bunch of extra info though that I might not cover in this tutorial. So like I said, all of the additional reading and stuff I will link in the description below, including this tutorial, where he drew some fantastic diagrams, runs you through a whole bunch of things, and how the network prediction stuff works, how the corrections work, basically how the stack works in a very nice visual format. I'll be running through the actual backend code to show you some of the stuff and show you the sort of the stack. Where does this information flow? What can you do with this information? How can you change this up? Why is this written as this way? All that kind of stuff. So I'll be running through all that kind of stuff in this tutorial. So if you're looking for some additional reading and to just really master this component, I completely recommend this little tutorial as well. Well, it's not a very little tutorial, it's a fantastic, massive tutorial. But definitely give us a look, and I'll be linking to the additional document as well in the description. So you can grab all those links below. And if you're curious about what that blueprint-only integration looks like, it actually comes from another fantastic developer by the name of Reddy-dev. And he also gave me permission to showcase this plugin that he put together, which uses the packed movement to create an incredible solution for teams that might be a little bit not too keen on the C++ side of things. That's all right, Every team has their own needs, and that's something we'll be covering as well, in terms of creating tools that empower different kinds of teams, as mentioned. So yeah, we'll run through this whole thing soon, but little preview of that here. But that might be in the next episode. This episode, as mentioned, we're going to just be covering the basics, understanding what the variables do, understanding the stack, all that kind of good stuff. So here we are in a clean C++ third-person template project. It's got everything set up here that you need just to sort of get going with your game and whatnot, but we're going to be exploring just what you get out the box. Let's see. You can see you got Quinn here, some nice little animations. You can move around. You can move up and down ramps. You can jump. And they even have some nice little extra features added for you, like the IK system, which you can see with the legs here. But importantly, we're going to just be looking at the character movement component stuff, right? The ability to jump, the ability to fall, interacting with objects, even bumping into physics objects and stuff like that. So let's go ahead and just open up the blueprint and see what we're starting off with. If you hit Control Space, open it up, the content browser, and let's head over to the third-person blueprint. As you can see, it's all set up in C++, so you won't see any blueprints here at the moment, but let's have a look. You can see it consists of a capsule, and importantly, the capsule is basically what you're driving around. It may look like you're running around with a character, but in reality, what you're bumping into and using is just the simple shape called a capsule. And attached to that is your mesh that has all the animation stuff running. But the animation system and the mesh itself, you can consider to be a complete separate entity almost. It's its own little system that, of course, uses the character movement component, but it's kind of separate from what we're doing today. So we won't be focusing on the animations and whatnot, but we will be just talking about the capsule and how to move it through an environment and interact with the environment. And of course, the camera and whatnot added in as well. But here's our favorite little thing, the point of discussion today, the character movement component. So as you could see when we were running around there, we were able to move around, go up and down slopes, stop, start, all that kind of stuff. So based on that, we can already start seeing that there's kind of like a pattern to how things operate in Unreal Engine, or in the character movement component. So what this means that you have input, which indicates player intent, which is then interpreted by the game engine and performs a physics interaction with the game environment to basically facilitate that player intent. And in this case, we can walk around, we can move up and down ramps, we can climb up and down stairs, you can fly, you can swim. There's a bunch of things that you can do based on what the player wants you to do. So of course, that segues nicely into what is known as movement modes. And these are the primary physics operations for moving a character around the environment in the character movement component. So let's dive into that, shall we? I've drawn up some very fancy diagrams here to demonstrate the various movement modes. Of course, we already demoed walking up and down slopes. We haven't necessarily seen a step up function where you move up and down stairs, or for example, little rocks and things in the geometry of your level that you'd want the player to climb over, without interfering with their movement. Those are all the things that the character movement component handles on its own. And of course, when you're running up and down ramps, you don't want them to necessarily climb a wall, or perhaps there's a slope that's a little too much of an incline for them to actually walk up, and therefore you'll start sliding down, or in this case, falling, and how it's coded currently in the character movement component. So of course, let's look at how that would work in the world. Like as mentioned, you have all these little rocks lying around, maybe you've got like little steps, and eventually you'll get to a slope. So you can kind of already see some variables there, right? Like you're going to have a step up height. How high up can the character step up when, I don't know, running into a rock, running into stairs, running into any kind of little obstacle on the ground? And of course, what happens when you hit a slope? Of course, the capsule's going to come in here, and you want to actually, instead of moving forward, even though the character's, the player's input is forward, it'll actually transform that by going up the slope based on a maximum slope height, which at the moment is about a 45-degree angle or so in the engine itself, by default. And when it comes to something like our little flying one, of course, now you add in vertical movement. You can go up and down as well. But flying is actually very, very similar to walking. It's just it's walking by a different name. And that's a pattern you'll see recurring throughout this function here, is that like a lot of this code is almost infinitely reusable for your own movement modes. We'll get into that though. So going back into that, flying does something very similar, except now, of course, you might be flying in the sky. But you might still run into something that you can potentially step up. It actually still does a little step up function check. It still allows you to slide up and down slopes, except of course it doesn't have that same functionality that checks if something's too high. In this case, if you're running into something with an angle, you'll just slowly slide up it depending on what kind of acceleration you have, or slowly slide down if that's the direction you're going in. That kind of stuff with flying. And when you get to something like falling, of course, that's when you just fall. And the entire time you're falling, it's going to be checking to see, oh, as I'm falling, have I landed on something that I can actually land on? Oh, I've touched a wall over here. Wait, that angle's too steep. That means I can't walk on this, therefore I'm still falling. I'll just be sliding along the wall. And eventually, when you hit even ground, or ground that you can feasibly walk on, you'll re-enter the walking movement mode. Moving on, we have the swimming. It's kind of, you don't always need to use this. I mean, a lot of games might not have swimming at all, but it's extremely nice to have if you do have bodies of water in your level. What's great about this is that like you can actually add in a physics field that is set to be basically a body of water, and upon entry, the system automatically enters swimming. Has a whole bunch of extra little functions like jumping up out of water, buoyancy, going up and down, but it still kind of functions in a similar way to the flying movement mode. If you think about it, you still have up and down movement, except now you just have the added element of being able to jump out of the water back onto land, and of course enter and exit a field, or a fluid, I guess, if you want to look at it more physically. The last kind of movement mode that's enabled or available by default is something called nav walking. This is an interesting one, because what happens here is that effectively it actually switches off collision with static and dynamic meshes on your capsule, and then just straight up follows a path. So it's almost like telling the system, okay, ignore any kind of objects, whatever the case is, that might fall along my path, adhere entirely to whatever the current navigation mesh is telling you to follow effectively. So I've never personally used this for anything, but it's there if you can think of a good use for it. I mean, there's probably actually are some good examples. You just want something, an AI entity or your character to move from point A to B without colliding with stuff, following a certain path. That's pretty useful, right? So there you go. Nav walking does that. Like I said, though, it's niche. I haven't used it personally. And of course, we might then move along to custom. You can have as many custom modes as you want, and this is great. You can just set up anything, as you can see here, like a parkour course, for example. I suppose the parkour system is something a completely different video entirely to talk about, but more important, it's decided to think about other kind of custom modes, such as wall running, right? That's a custom movement mode. Wall sliding, just sliding on the ground, like you would like do a cool little battle slide, slide down a hill, things like that. Those are all custom movement modes, and we can make as many of those as we want. And how all this works is unreal, that it just constantly switches between different modes based on what you set up in your logic. You can go from walking to flying to falling at any given moment based on what's going on in the game. Or I guess based on player intent. Perhaps the player can push a button to enter flying, and bam, there you go, they're flying, stuff like that. So that's kind of how the basics kind of work. The kind of the pattern in the character movement component is that you'll always have a physics function, walking, flying, whatever the case is, but you'll be swapping between them. And that's kind of how the system wants you to basically implement your logic. They want you to create new movement modes whenever you're thinking about something else. But to be honest, that's something that's mostly doable in C++. But as mentioned, we'll be getting to some cool little things later on that allow you to very easily do this kind of stuff in Blueprints entirely as well. But we'll get into that plugin at a later stage. For now, let's focus on the C++ over here, right? And by the way, if you're interested in just the Blueprint stuff, I still recommend just watching this video, just going through the C++ with me, because it's important to know what happens on the back end, where things are, so that you can then see, oh, this is why we do things here and here and here in Blueprints later. So now that we're done with this fancy little demonstration over here, let's hop into the engine again. So we discussed some stuff there, right? We said, okay, we'll play end-to-end, you can move forward, there's a little physics operation, but when it comes to the actual variables itself, here, look, here's that max step height we just talked about. Oh, now that allows you to move up and down objects, so therefore, if you don't want the player to step up too high, you can drop this down. If you don't want them to step up at all, you can hit it at 0. And bam, you've got some additional functionality there. By setting this to 0, suddenly you can't step up anything. You can only slide along things, so therefore, maybe that's a desirable effect for you. And here are some important variables as well. So we discussed sort of like how the player moves up and down stuff, that they can slide and do all this kind of stuff. But of course, we haven't talked about some of the most important functions in the character movement component, or rather, the most important variables. Let's head over here. So basically, this is now physics, right? Typical physics, you get acceleration. That's supposed to be an A. I hope you can see that's an A. You get velocity. Oh no, I shouldn't have done this with writing. My handwriting's terrible, but here we go. We're gonna keep going, all right? And of course, you get speed. In the character movement component, you can consider these two to be vectors. So therefore they have 3 different values, right? X, Y, Z. Oh my goodness. I should be typing this out. Anyway, you get the idea. They're vectors, right? Speed. Typically when you're talking about speed, it might be something you see in animation systems, all that kind of stuff. It's a scalar. So let's say 400 being 400 centimeters per second, right? Because the engine uses centimeters by default. So, for example, you might be wanting to move 400 centimeters in a certain vector direction, and therefore, that's what you get. So that's why when people talk about speed, they're often talking about the scalar. So how does this translate into what we're working on over here? Well, here we have max walk speed, right? Max crouch speed, because of course you can crouch too in the engine. And then you get little extra things, like there's a lot of variables to go through over here. But if you're wondering what min analog walk speed is, basically depending on what's the minimum amount of like speed you want to be going at, right? When you're just doing a little bit of movement on an analog controller. That's what you want here, because obviously you don't want the player to slow down to micro levels of movement, because then the animations are going to look bad, all that kind of stuff. So that's why stuff like that exists. And of course, the other important variable, braking deceleration. So we're just talking about acceleration, right? Simple enough, deceleration is just the opposite of acceleration. So how it works in the engine is that you would have player input, which will be adding an input vector. And effectively, that's almost like your acceleration. Which direction does the player want to go in? What input direction are we going in? Velocity will just be the accumulation of acceleration over a number of frames. And of course, speed, would, like I said, is just typically our standardized how fast are you going kind of thing. Not necessarily which direction, just how fast. So max speed over here indicates what's the maximum speed I want to go to before we should, stop effectively. We don't want to accelerate infinitely. The player's not going to be just like going to light speed after just hitting W for a small while. We want to slow down and stop at some point at a maximum threshold. That's what this is. A max speed of, well, you can see there is 500 at the moment by default. So that means we're going to accelerate every frame in the direction of acceleration up to a maximum of 500 units in that direction. Now what happens if we let go of W? Well, now we're going to have deceleration, right? And of course, deceleration is kind of self-explanatory. It's the opposite of acceleration. So once we want to basically slow down to a stop, there's more than one variable that dictates how fast you stop in the character movement component. Let's have a look. So this is one inconsistency, right? Is that you can often change the movement of the various modes, but acceleration is kind of standardized over here in max acceleration, which is interesting. And what this means is that you basically be speeding up at the same rate regardless of which movement mode you're in, which can be desirable. Of course, you can extend this logic to have acceleration rates for different movement modes as well, which I've done previously, but that's up to you. Depends on what your project needs are. But you can imagine now that 1500 max acceleration indicates that you'll be moving basically 1500 centimeters per second faster every second, right? Simple enough. But that means it's almost an instantaneous reaction, which can be very desirable, especially when you change directions and stuff like that. It can be quite a desirable effect to have, to be able to change directions and get up to speed very quickly. But to show that this is actually, working as intended, let's go 100. So therefore, 100 centimeters per second every second with a max speed of 500, right? Indicates that we'll be hitting max speed in 5 seconds. Let's go. This is going to be very slow. Let me go straight. So 1, 2, 3, 4, 5, and now we're finally up to max speed. But if I change directions, you can see it almost has to start again, because we're not transforming our acceleration velocity when we change the rotation of the character, right? So if I change directions, I'll have to start the speed up basically all over again, depending on how much of, I guess, the energy, the forward momentum is transformed into the new direction. So we're pretty much back up to full speed again here. So you can see that's how you can kind of balance and adjust your game. So it feels good to get up to speed really quickly, so that's why 1500 is the standard by default. But you can change that. You can change that based on your needs. You can do a lot. And as mentioned, you can modify and extend this to have different acceleration values for different movement modes. It's quite nice. Like the character movement component is basically the world's your oyster. You can do whatever you want with it. You can change it. There's a lot of things exposed to you that you can just straight up change and modify. But you're probably wondering, right? Like if we have like we demonstrated previously, if we have 100 centimeters per second, hold on, why isn't ground friction actually affecting this? Because in normal physics, ground friction will affect how fast something speeds up. Well, in the character movement component, friction effectively only works when there's no acceleration, which means that friction and braking deceleration kind of work together in this weird way. So that's why it's important to know what these values do so that you can modify them and change them. Because, for example, in flying and falling, there actually isn't really any friction being applied whatsoever. So you might have an inconsistent feeling between walking, flying, all that kind of stuff, which is what you might want. But, maybe it's not what you want. So basically, when there's no acceleration, no player input, whatever the case may be, then deceleration will kick in as well as friction. But walking has friction in the form of ground friction. However, going up here, you're probably wondering, what is this friction value over here? And what does this use separate braking friction mean? So here you can see that actually you can see these all reset it back to default, right? So this character movement component here in the C++ example, I guess in all examples, is slightly modified. So at the moment, it is using this friction value over here for all the movement modes, which means currently there's actually no braking friction whatsoever applied to any of the movement modes, which I actually think is best. I'd seriously dislike having this random friction function when the deceleration values are actually a bit easier to balance, because adding in friction just causes nonsense. So I agree with what Epic did here in terms of just use separate braking function and set friction to 0. Trust me, that is my favorite way of doing it. But if you were to enable it, or for example, if you were to disable this now, it would then go ahead and use the separate friction, the friction value. So then ground friction will apply at 8, whatever that means. I mean, you can go play around with these values, like the friction values, like I said, but in the end of the day, it makes far more sense to just use acceleration and deceleration. Because think about it, right? If you add in braking friction, or I guess any kind of friction at this point, it adds in an element where it's just, I don't know, it's a bit arbitrary, right? Like you can just add in a little bit of extra braking force. But if you have the acceleration set at 1500 and you have deceleration set at 1500, that means you're going to accelerate and decelerate at the exact same rate, which makes it far, far easier to balance out your movement. Because, I don't know, adding in this random value that doesn't even make too much sense. It's just, I don't know. It might come in handy when you really need to fine-tune your frictional values and get the physics just right. But in all honesty, acceleration and then deceleration braking force, those are the most important things. Because if you think about it, if you want to accelerate at 500 but decelerate at 250, which means you're going to immediately get up to speed in 1 second and you're going to slow down to 0 in 2 seconds. That makes far, far more sense. And it's far easier to understand. So yeah, like I said, I like what Epic did here. Use separate braking function, set friction to 0. Just ignore that nonsense. That's just, most games won't need that. You're going to have a far better time just using the acceleration. So that's one big tip already. If you want to see this in action, let's say we want to see how the acceleration, deceleration works. Well, let's say now we're using separate braking function, right? We set friction to 0. So that means 500, we'll get up to speed in 1 second. We go to our walking movement mode over here. We set braking deceleration to 250. Now, theoretically, it should speed up in 1 second and slow down in 2 to 0, right? Let's watch this happen. So, 1 second, up to speed, stop, 1, 2, we're at 0. Way better. That friction value, it can go somewhere else. Like, I don't want it, you don't want it probably. Someone might want it, but none of us really want it. So, do what the Epic did here and just turn that nonsense off and live a happier life. Alrighty, so that's the gist of it, right? So as you can see, you got your max value, you got your acceleration that gets up to max speed, and then you get a deceleration value that gets you back down to 0. But importantly, that max speed value, obviously there are things that can push you above your max speed. And you don't want to just cap the player's movement speed. If you do want to cap the player's movement speed entirely to 500 of cases, you can. You just need to extend the component to do that. But in this case, it's desirable to basically want to hit a speed boost for temporarily, or perhaps you get like booped forward by a launch, like a little launch pad boops you forward and stuff like that. Whatever the case may be, you do just kind of want to slow back down to your normal speed after a certain time, right? So therefore, your deceleration once again come in handy, because basically what happens is if you ever exceed your max speed, deceleration will kick in and bring you back down to your max speed. Of course, at a deceleration of 2000, it's almost instantaneous. You stop and start like pretty quickly in this example. Let's just go. These are the default values again, right? Almost an instantaneous stop, right? Which actually feels good in this case, but you might want to change that up. So yeah, imagine that now. So basically, if you ever were to go above your max speed, it would actually drop down to your max speed pretty quick. Effectively, you have set a hard cap at 500 because it's very difficult to get above that hard cap of 500. But that's how it works, right? So therefore, deceleration affects not only when you let go of movement or input when there's no acceleration, but also when you go above your max speed threshold. So yeah, these are the variables, like I said, you can change and set and play around with. So already you got a lot of power here, right? Like what I've demonstrated already, you can change up a lot of stuff. You can get a lot of usability out of this already. You can start building stuff up. I suppose the only things we haven't really touched on yet that are also extremely important for game feel, gravity scale. Oh, this is great. So gravity scale, let's go back into the game over here, right? So it just affects how much force you need to go up in the air, obviously, and then obviously how slowly or how fast you fall back down to Earth. This is pretty floaty, right? Which can be desirable, like no issue really, but it's pretty floaty. Let's say you want to change that up, like like a common little tip or little trick is that setting gravity scale for 4 to 4, for whatever reason, just feels pretty good. Like it's a pretty good value. You might want to just play around the 4 value, and then of course we're gonna run into an issue now where if we try to jump with our previous jumps like height, we get barely a jump in, which means once we change that gravity scale value, all of our, well, more important, just our jump force needs to change. But if you have something like launch pads in your game, stuff like that, obviously they'll have to change their velocities. So you can kind of see how game dev can be this balancing act of like, oh, if I change this one thing, it's got a cascading effect on a lot of other things. So that's why you got to be kind of understand where things are and also what affects what. So be sure to work with your team members when you change values. Don't just change something without anyone's knowledge, especially something as important as gravity scale, because that affects a lot of values. One value, like I said, has a cascading effect, which is also kind of important to know as a gameplay programmer, like what can you do, what kind of tools can you build to facilitate these changes, and therefore basically possibly once something changes, change a whole bunch of other values in parallel to prevent that from happening, where like if a designer or someone else or someone who might not know what's going on, or so if rather just someone who doesn't know that they're causing a big effect, if they change that value, all the other values will also change and update independently as well. So that's a tool that you can build. So now you're beginning to maybe think like a gameplay programmer. Oh, here's a potential shortfall. Yeah, what kind of tool can we build to make it better? How can we support design? How can we support the team in better ways? So yeah, that's something to keep in mind. But anyway, back to the topic at hand, which is the character movement component, right? So we've now changed the gravity scale to 4, which means we fall a lot faster, which means we also need to now jump a lot higher, right? So let's go down to our jumping falling settings. Look at that. Jump Z velocity right here. Bang, 700. Let's more than double that. We've more than doubled the gravity scale, so we might actually need more than a double. So let's just check how that feels. Once again, just a balancing act at this point. This is just a feel thing. Ooh, it's quite a jump, but like it's maybe a little bit high, but it feels good. And also, if you have a weightier gravity scale, I think having a weightier land animation will also sell it. So this is how you can balance your game and get the right feel out. But yeah, the scales are really feeling a lot better. Let's go ahead and play around with that some more. It feels a bit high, right? Let's just try 1200. Yeah, that feels a lot better. It's maybe you can go a little bit higher than this. It depends on what kind of game you're making, right? But it really feels a lot better. As I said, changing the land animation to be a bit weightier, it'll look better. It'll feel better. And that's basically how you can start working on your game feel. But back to the variables. Getting a little sidetracked once again. Ah, yes, right. So, air control. So let's say you're falling, right? In the falling movement mode, you might want to give the player some control over their horizontal movement. For example, they're in the air, they want to miss it, they want to hit a jump. Oh no, they want to change direction, that kind of stuff. You want to give the player some control over their eddy descent. So let's just go ahead and demonstrate that with, let's just make it a bit floatier again. This is going to be, let's keep you at 1,000 though, just to get you further up in the air so we can demonstrate how air control works. So by default, it's at 0.35. So basically, 35% of your usual input will still allow you to move. But you can see it's very little. Especially if you want to change direction, it's very hard to change direction. But if you want to move forward and get a little bit more forward, for example, if I was to just jump, it's a bit floaty, so it works properly. Bad example. But I can now for example, jump up and move forward a little bit, if I intend to, right? So that's an example of just how air control more or less works. So of course, now you could change that completely. You can come in here and you can be like, okay, I want to give the player full control, 35%, no ways, 1.0, 100%. So now they can actually move around as though they were moving around on the ground, basically. You have far more control over where you're going, where you're landing, which could be exactly what you want. Maybe you have a platformer. You want to give the player a bunch of control. Oh, for example, there, like I jumped off the cliff. No, I don't want to actually jump off the cliff. Let's go back. So there you can see how gravity scale, air control, jump force, all these things kind of all contribute to one another to get your game feel, which is why depending on what game you're making, all these variables really matter. And you can kind of see now how you can play around with these to get that exact feel just right. And then if you add the animation layer on top of that, oh, you get the feel just right. It feels so good. Anyway. Back to what we're doing. I'm sorry, the stuff is exciting. Okay, you have the tools of creation at your fingertips here. You can do so much. You can create so much with just this component alone. You can add in all the other systems and make some incredible stuff. That's why it's important to get the fundamentals down. I mean, movement, right? Movement is one of probably the most important things you can get in the game. You play, let's say, a Naughty Dog game. That movement feels so grounded and so natural thanks to how, first of all, the movement system put up, but then also how the animation fidelity and stuff kicks into it. You play a platformer, let's say, like a Mario game, you want precision, you want the jump to feel right, you want to be able to have a certain amount of air control, you want to land just right, you want to do, maybe in some platforms, some wall jumps, things like that. These are all things that you can create and balance using a component like this. And based on all those variables and things we just went over, and also some of the crazy drawing stuff we did previously, you kind of see why it can be so difficult to create your own component, because I mean, this is the easy stuff, right? These are just the variables and you can change to affect things. But remember, what's going on in the background is that the system's busy tracing the environment, to figuring out, oh, I've penetrated geometry, depenetrate out back to this point, or I guess it'll be closer to like that point, whatever the case is, and all that kind of stuff. So there's a lot more going on in the background that's sort of just done for you. And of course, as mentioned right in the beginning of the video, you can be standing on a moving platform and you'll move with it. Stuff like that it's kind of tricky to get right on your own, and it's just nice to have a component like this really set up for you that you could just extend and modify rather than just trying to build your own from scratch, because that could take you a long time, especially to get it just right. And if you think about it, this component is pretty much battle tested. It's more or less what Fortnite uses. It's more or less what most Unreal Engine games use as the baseline is this component. So learning it, getting to terms with it, even though some things you might not like. I mean, there's a lot of people have a lot of gripes with this component based on just a few decisions and stuff like that. But like, it's just something you live with. Like I said, you can always go and create your own component if you really, really, really want to. But if you are an indie developer, even if you're a AAA developer, this is the supported function, the supported component. You kind of want to like get to grips with this and just learn to handle it. And like I said, the royalty oyster, you can create tools. I mentioned you can create a tool that when the designer changes a certain value, other values all change independently based on that. Things like that, like there's so much you can do and extend that can allow you to fine tune your own project. But this is a fantastic baseline, because remember, even the multiplayer aspect is already built into the function. It's a bit tricky to get the multiplayer stuff to work properly, like admittedly, but we're going to go over that soon as well, and then it hopefully won't be such a scary beast anymore. But yeah, this is a great function, and when you learn this thing, you can do so much with it. So I guess now, after all these little things we just played around with, there's a lot of other variables here, but if you just read through them, read the comments on them, you'll understand what they all do. But those are the most important ones. Those are the real meat and gravy of the component, is what we just went through there. The movement modes, and then the variables that drive them, and also how they work. Alrighty, so now that we've been through some of the little variables over here in the blueprint, let's go ahead and just look at some of the C++. Now remember, if you're here for the blueprint stuff, I recommend just checking out the C++ stuff anyway. You can see the flow, how things work. And if you're here for the C++ stuff, well, your section has begun. Let's get into it, shall we? Here's a Visual Studio instance that came alongside it. Now remember, because we started up a project with C++, all of our little character stuff actually is done over here. Let's open it up, shall we? So here's the character. You can see, there's the camera and stuff that's been added. All the other things that came with the character actually come with the normal A character class. But you can kind of see some of the new enhanced input stuff over here, such as the jump action, move action, and it's all done here in the character itself. You'd actually typically want to do this kind of stuff in a separate component, like an input component. An example of that is something like the hero component that you'll find in Lyra, which once again you can look at to see some of the better ways of doing things. I just wanted to show where all the setup is done in C++ over here. So you can see over here, on begin play, you add the mapping context like you would in Blueprint. You've maybe seen an example of that in the blueprints. And of course, then you would bind all the actions to your corresponding function in C++ over here. But we're not here for the character at the moment. What we're here for, if you hit Control T and just look for UCharacterMovementComponent, here we go. If you ever want to just like get straight to the CPP option, just go, you can right click and go to definition and open up the CPP as well. And once you've got that set up, let's go have a look through it, right? Like, as you can see, this component is gigantic. Just the .h file, the header file, has so much setup. And the CPP, what does it have? About, what, 8,000, almost 10,000 lines of code nearly? Yeah, well over actually 10,000 after some recent changes. So there's no wonder why you can probably get lost in there and why it takes so long to kind of really learn the ins and outs of this component. But don't worry, we're going to run through some of the most important stuff. A lot of the stuff is good to look at, but in reality, like I said, there's actually a pattern to what you would do as a designer or a programmer, and we're going to get into that kind of stuff. So where do you begin, right? Well, we really can see some familiar stuff. We can see, oh, there's the gravity scale. Oh, there's the max step height. And you can be like, oh, well, this is a good jumping off point. We can kind of see where those are used. But of course, we also have the max speeds. And importantly, we've just found like an incredibly important function. For example, if you ever want to change speeds, add in like a sprint speed, stuff like that, you'll probably want to look into this function over here. So let's just go ahead and like look into it, right? As you can see, depending on which movement mode you're in, you're going to want to use a certain variable. So of course, max walk speed, we've been there, we've done that. That's the ground speed, we've got the flying speed, swim speed, and all of them have their own little section here, right? And all it does is just grab the current movement mode, does a little switch statement. Easy enough, right? Unfortunately, we're quite familiar with the different movement modes now, right? We understand the fundamentals of how they work. But of course, what triggers them? Where do they come from? Where do they go? Let's go up here. Just scroll up a little bit and you'll see something called the Start New Physics. And, well, there's a good little jumping off point. So, as we talked about, when you have a little input action, obviously it's going to go into what we call a physics function. And that's all that this is. Very nice, self-explanatory, phys walking, phys nav walking, phys falling, all that little favorites we talked about, all done here. Once again, just using a little switch statement. Easy enough, right? Movement modes are your best friend. That's what you're going to use in this character movement component oftentimes. But like, we're kind of jumping a little bit ahead here, right? I just wanted to show you more or less where these various modes are used. But now, where's this called? Well, if you ever want to find anything in a component, well, a good place to start would typically be the tick component, right? Or rather, it's tick function. Let's go ahead and hit Control T. You get M for members, and let's go find the tick component. Take us straight there. Now, remember that what we said earlier about how there's like kind of like a pattern, right? So the player would have an input indicating player intent, and then we'd handle that. So that's basically what this does here. So here's a tick component, right? Does a bunch of little checks and whatnot, but the most important thing is we are consuming that input vector that is coming from the player. And effectively, the input vector can be just any vector in any direction. But of course, if you're walking on the ground, it would probably ignore, vertical movement. It would just do horizontal. But if you're flying, it could be any direction. So whatever input you give to the add movement input function in Blueprint or in C++, that's basically what gets sent over here and then consumed. And once it's consumed, it knows exactly, okay, this is our input vector for this particular tick. How are we going to handle this? Oh, what kind of acceleration do we expect from this tick? Is it 0? Is it actually a bit of input? Can we actually accelerate? All that kind of stuff. But let's move on through this little tick component over here. So you might have started seeing some little async things going on over here, whether or not you're using an async tick and things like that. So this is mostly to do with something called an async root motion task and how that's handled in the engine. You'll see examples of that in Lyra, how they do their dash mechanic. It's actually very, very cool. And I suppose we can talk about that a little bit now with root motion. Basically, if you're not familiar with root motion, it's effectively how an animation is authored to allow you to basically move with whatever the animation is currently doing. Basically, when its root bone moves, the character will want to move in the exact same way. And the character movement component facilitates this action and applies all of its cool physics stuff to the arc of motion provided by an animation asset. That's a lot of gobbledygook I just said, so unfortunately I don't have an example of this, but effectively, you know what? Let's open up Paint, shall we? Good old Paint. So effectively, imagine that's your character. Whoo boy, your brilliantly designed character. And let's say that the root bone is located over here somewhere, and that's where all the other bones extend from. So now, if you animate, and you make the root bone move with the animation over a little arc along the way, what the character movement component wants to do is basically take that motion data and effectively transform that almost into the input vector we had before, except it's a separate system in root motion. And what's nice about root motion is that it is fundamentally networked within the character movement component already, which makes it pretty desirable, right? But of course, like, if we can extract root motion data from an animation, surely we can just tell it, hey, here's some nonsense, hey, here's a root motion task. I want you to make up root motion information and then just follow that arc. So therefore you can be like, oh, I want you to move the root over in a straight line for a certain amount of time, and that could be your async root motion task. And I guess an example of this is in Lyra. We won't get too much into root motion stuff at this time in this tutorial, but that's basically how it works. Like I said, possibly future tutorial might just look into gameplay ability stuff and then start talking about that root motion stuff that we just said, the async root motion stuff. But you should be familiar with root motion animations already, hopefully. But let's move on, shall we? Back to the code at hand. So now we've spoken about the root motion stuff a little bit, touched on it, and I can kind of see what this async stuff is talking about. So let's move on along the way. Here it talks about simulating physics. So basically, obviously, the character movement component, importantly, is almost like its own physics simulation on its own. It doesn't necessarily interact with the physics system of the engine. I know that might sound confusing, but effectively you get physics. It might be, well, previously it was PhysX, now it's chaos in Unreal Engine 5. That runs on a completely separate system almost. This component can interact with physics, but effectively, if you are simulating physics, in other words, letting the physics engine control the character or its capsule or its root, you don't want to be running any of this code, because this code is in essence its own physical simulation. And this is important because of the multiplayer stuff that we're going to be going into. And to touch on that just a little bit, effectively, networking real physics is extremely difficult. It's a very difficult topic in the field in its entirety. It requires stuff like having a fixed simulation tick, ensuring that everything syncs up properly between client and server, having rollback support for that stuff. It's a complete nightmare, which is why you don't see a lot of that in most networked games. I mean, you might see a little bit of physics interaction, right, that's networked, but it might be a little hacky or something. It's something very difficult to get right. We're seeing more and more of it though, like some pretty substantial leaps. I mean, I know Epic themselves were working on some sort of functionality for networking physics, but it's currently a little bit floating in the water, a little bit dead in the water, not really, you know. But we'll see where that goes in the future. But for now, so you can see why you would not want to simulate physics and run this component at the same time, because they're both basically trying to take control of the root of the character and do their own thing in their own way. And one way is networked, and the other way isn't really networked at all, for the reasons as mentioned before. If we scroll down a little bit, we can see something called the avoidance lock timer. There's an avoidance system built into the CMC, and you can play around with it if you want to, but we're not going to be covering that right now, but that's just what that refers to over there. Here we're going to get into something with the networking stuff. Episode 2 is going to be the big networking episode where we actually do the important stuff. The actual, like, oh, this is how you implement network prediction. This is why you do things in a certain way. We'll get into that. But for the time being, let's have a quick little look into what's going on over here. So obviously you can see role simulated proxy. What does this mean exactly? So let's just go ahead and click on that variable and hit F12 and see where it's defined. Here's all the various roles. Of course, like every enum, there's a none role. Don't worry about that. But then you can see stuff like simulated proxy, autonomous proxy, authority, and little descriptors here. So basically, simulated proxy, as you can see, is a simulated proxy of this actor, the locally simulated proxy. Autonomous proxy is the locally autonomous proxy. These comments are not very helpful, as you can see. So effectively what all this means though is that a simulated proxy on your, effectively, if you imagine the client server setup, right? You're the client. What you see around you, all the other players, they're effectively like ghosts, right? They're called simulated proxies. all they do is receive updates from the server with like velocity and stuff like that, and then extrapolate a little bit on that information. But as I mentioned, they are ghosts. They are echoes of the past sent to us from the server. Because you, as a local client, are always in the future, air quotes. Because you are constantly processing ahead of the server to make it seem like you have full control. But the server, being authority, has the real final say over the current game state for all players. So while you, as the autonomous proxy, might be processing ahead of the server, if something goes wrong on your screen, or you try and cheat, or something along those lines, the server can correct you and say, no, you're talking nonsense, I'm the real big boss over here, and then rewind you back and let you continue on. So that's the roles here. The simulated proxies are the other players on your screen that are just ghosts, they're shells. They just receive updates and pretend like they're real. And those are the things that you interact with. The autonomous proxy is your local little client, your little pawn, and you have full control over them to an extent, because whatever you do, the server tries to redo, and if it does something incorrectly, like for example, if something happened on the server side, such as a box flew in from the side and suddenly interrupted your movement, but you didn't see that on your side yet because you have like maybe a little bit of lag, well, the server will be like, okay, this happened, this is the real state, and then rewind you back so that you actually hit the box, for example. I'm going to also actually link a really great video from the Overwatch developers on how this works. Their setup is amazing. It's different to Unreal. They use an ECS, Entity Component System setup, in their netcode and whatnot. But the fundamentals of how all this works, as well as how you should be rewinding things and all that kind of stuff, that's all there in that video, and that's very important. So I'll link that below, as well as mention it once again in the next episode. But now you can kind of see what these various roles are, right? So that basically, let's just have a look at a little example. I've taken a screenshot here of basically a multiplayer setup. At the top here, you have the server, and it's a listen server. What listen server means, that's a net mode. Perhaps we should quickly dive into the net modes to have a quick little look. Luckily, we have one right here. Click on that variable, hit F12. Here are the various net modes. Standalone, as mentioned, it's basically, it's almost a single player game or a local co-op game. You know, a little split screen type thing, not necessarily split screen, but a couple of local players, no real multiplayer functionality, but it's still considered to be the server in this case. And of course, dedicated server, pretty self-explanatory. Basically how you play most AAA games nowadays, AAA multiplayer games. And then you get listen servers. It's when you host a game, you know, as your own little client on your PC, and then all your friends can join your game. That's basically a listen server. And you can probably imagine or even think of a few games that maybe offer a way to host listen servers as well as dedicated servers. I mean, look at something like Valheim, you know, survival craft type games like that. Those can be either or. And, I mean, whatever works for your game, you know, whatever works for your project. But what's important here is that you can kind of see why these roles are important and why it could be important to understand why you'd ping a certain role, like check to see, am I on a dedicated server, am I a listen server, or am I a client? And of course, client is self-explanatory, right? You just connect, you're a client connected to a listen server or a dedicated server, effectively. So those are all the different roles, right? Basically, fully explained it. The reason I went over this in this video is just so you can see why certain things are called in certain places. Like here, your role is greater than role simulated proxy means, well, if I'm an autonomous proxy, which means I'm simulating my client locally, I'm that particular pawn, or I'm the server, run this code. And of course, it does a whole bunch of things. For example, like I said, the server can potentially ask the client to perform an update if it disagrees with it. And of course, if I am locally controlled, whether that be a listen server playing as a pawn, because in that case, remember, you're hosting a game locally, which means you can be the server, but also controlling an entity, an actor, a pawn. So therefore, you want to move the character, and that's when we use that little input vector, and then actually performs the move on the local character. And so over here, you can see get remote role, and over here, get local role. So that's pretty self-explanatory, right? Basically, what is my role on the remote server, and what is my role locally? And oftentimes, this is for this particular pawn, right? Remember, this component is attached to everything. It's attached to simulated proxies on your side. It's attached to your local player. And on the server side, it's attached to all of the other entities as well. So that's why it's important to have this code here, which check. So in this case, for example, if if my local role is autonomous proxy, then effectively my remote role will be authority, because the server always has authorities. So to sort of like understand these roles a little bit better, well, local versus remote, here's a little image that I put together. So as mentioned before, this is the listen server, right? And as you can see, I am authority, and the listen server can own its own pawn and move around the environment. And technically, the two things you see, the two clients that are connected on the server side, are simulated proxies in terms of how you'd want to perform certain logic, but their remote role is still going to be autonomous proxy, which means they are controlled by other players on the network. And of course, locally, your local client is going to be the autonomous proxy. Your remote role will be authority, because remember, the server owns and controls the game, which is why your remote role, even these, the simulated proxies, their remote roles will be authority as well, because the server ultimately controls the final state of the game and just sends information back and forth between the different clients, and even corrects your local simulation, for example. So that's important to keep in mind here. So you can see why it can be a little bit confusing at first to get into this, understand where these roles are, and also understand the difference between a local role and a remote role. But once you get the hang of it, it becomes relatively simple to sort of grasp why certain things work the way they do, and how you can use this information to build your games for a networked environment. So returning to the image quickly, you can kind of see these are the ghosts, the echoes of the server over here, the simulated proxies, the other clients. This is you, the autonomous proxy. On the server side, you are a simulated proxy in a sense, but also your remote role is autonomous. And what's important about this is that this particular view right here is why you would want to consider these as simulated proxies on the server side, even though they are the authority. Because this is a listen server, that means it's currently simulating the game in real time alongside the clients. And remember, these simulated proxies, they're ghosts, right? Remember, they receive updates from the server at a certain tick interval. And that's maybe what you've heard before. There's something called the tick rate of the server. And effectively, the clients also have a tick rate, right? Like, for example, Fortnite at one stage had a server tick rate of 60 Hertz, which means 60 updates per second sent to the clients. And the clients updated at 72 Hertz, 72 ticks per second. And of course, if you're only receiving a positional updates in between basically a couple of ticks of a frame, you're not going to be receiving a very smooth image. So every single time you receive an update from the server, what it'll do is it'll say, okay, this is the new position, the new velocity, all that kind of stuff. And then it'll kind of interpolate, or in this case, on the client side, extrapolate to allow the client to move smoothly on your side, to allow the simulated proxy to just move in a smooth rate. Otherwise, you can imagine you'd see them teleport, bang, 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 all the time. It will look a little bit bad. And the same thing occurs on a listen server, because remember, the clients are sending updates at a certain tick interval as well, that does not match the local, basically, imagine the tick rate, the frame rate of the computer. So therefore, you want to interpolate between frames, something called network smoothing. So that's why you'll see that term pop up over here at some point. Right here, in fact. That's good timing. Smooth client position. So you can see why you'd want this to run on both a client, like an autonomous proxy side, as well as on a listen server. You can see very specific listen server, because that would just be a waste to run extra logic on a dedicated server, because it's not actually simulating the game in real time alongside the clients, correct? It only cares about the updates. At this particular point in time, what happened? Resimulate that point in time. Did it actually occur? Yes, no. Send updates to the clients, correct any mistakes, and keep everything in a happy little state here on my side. That's what the server does. So that's why we only perform this logic on a listen server, because it's currently operating almost like a client and a server at the same time. But we want to skip all this extra stuff on a dedicated server to save resources. Important information. In fact, if we scope over to this function, it actually doubles down. It says, no, definitely do not run on a dedicated server, do not run on standalone, because you don't need to smooth the client, or you don't need to smooth simulated proxies on either of those entities. However, once again, if, for example, the client is a role simulated proxy, or remote role autonomous proxy, which means a simulated proxy on a listen server, then yes, go ahead, smooth and whatever the case is. And remember, when you smooth the visual, basically all you're doing here is smoothing the visuals of the simulated proxy. Not necessarily, adding any extra information necessarily. You're just smoothing the visuals from whatever the server tells you to do. And if you're on the server, obviously, you're just smoothing the visual, whatever's coming through from the client. So let's go back up to the function again. You can just hit back. So once again, we have some more conditional logic. You know how you can, I mentioned briefly that you can crouch. The character movement component allows you to crouch as a character. Effectively, you're just shrinking the capsule size by about half, right? So remember now, some information is sent through to simulated proxies, aka, the ghosts, and some information is not. This can almost be considered a bit of extra logic, because technically, remember, you're not necessarily crouching every single frame, whereas every single frame you do need to update velocity, you do need to update positional information. So now you can kind of see how you can optimize around that. Be like, okay, we're going to just flip-flop this boolean and send that through to the simulated proxies, and when they detect that, all they'll do is just do the little proxy capsule size adjustment on their end, and so on and so forth. Because like I mentioned, that doesn't necessarily happen every frame, and you want to minimize how much stuff you're sending between client and server in this case. By the way, I apologize. We did get a little bit more into networking stuff in this episode than expected, but it's a good thing, because now we can sort of build on it from here. Yeah, we're on this adventure together, right? So let's go ahead and keep on going. And after doing that, it just does a simulated tick, which, as mentioned, just does a little thing where it extrapolates on the information provided by the server. You can read through the code, and you can see if you can understand all the bits and pieces, but if you're doing more advanced stuff, you might need to change some of this in here, but honestly, most of the time you won't need to change too much in here, unless, like mentioned, you're doing a little bit of extra stuff that you need to extrapolate on based on information from the server. But that just depends on your project. Right, let's get back to the tick. We're done with the tick function, and then we'll get into the most important bits and pieces, right? And then, of course, mention the avoidance stuff, which just updates the avoidance. But as mentioned, not too important. Don't really use the avoidance in the character move component that often. And then we have this little section over here, which, remember, this allowed us to boop into those boxes that were available in the level. Immediately open up the level. These little boxes here. Because remember, these are actually using the physics of the engine to move around. So this little bit here allows us to basically interact with physics objects from the character movement component. So here, for example, you can apply a downward force by standing on something potentially, or apply a repulsion force if you're supposed to, if you're walking into something, or however you set it up, basically. And bam, we're basically done here. All this here is just a bit of visualizing of the movement, so that's just a little debug thingy for you to play around with if you want to visualize what's going on. But yeah, that's basically the tick component. And well, what did we run into? We realized that it does a few things, right? All it really does is just consume. I went too far. There we go. Consume the input. Remember the intent from the player. Then basically handles this. And remember this intent, this vector, is actually sent across the network. It's one of the few things that are sent through the network. And based on that information, it then goes ahead and does all of its things. Like I said, it could do an async tick with weird root motion stuff. We're not too interested in that at the moment. But beyond that, depending on what we are we autonomous proxy? Are we authority? Are we a simulated proxy? It has a bunch of different logic. And that logic just entails, okay, if I have intent to move, and I can move, apply acceleration. And if I have acceleration, therefore I should be changing my velocity. And if I'm applying velocity, how do I interact with the environment? And what does the environment impart back on me to reduce my velocity, to prevent me from moving forward? I can't move through walls, all that kind of stuff. And that's what all these ticks do. So let's have a look at what's mentioned. One of the important things here is the control character move. And in this section here, what does it do? We're just either going to perform the movement locally if we are the authority, or if we are an autonomous proxy running locally, and we are, well, in this case, a client, well then obviously we want to just replicate our move back to the server, as well as simulate that move locally. Because remember, that I told you previously, is that you're kind of in the future as a client, right? You're busy basically simulating ahead of the server because of, lag compensation and all that kind of stuff. So once you've performed your move locally, you're also sending through your current state to the server, and then it can replay your move on its side, or rather simulated move at that timestamp, and then figure out, okay, did you move correctly? Was there anything you didn't know about that I need to change and fix by doing a correction? That's all handled here in the replicate move to server. But we're kind of just most interested in what happens in the perform movement, because that's the big granddaddy over here. The big function that does most of the things you need to worry about. Perform movement is what actually does most of your actual movement logic. It calls the physics functions, it does a whole bunch of stuff. We're going to run through that quickly. And one cool thing about this is that we're actually pretty close to getting through the full loop, the main pattern of how this character movement component works. So let's get back into it. So beginning off, you can kind of just see the basic checks. Make sure that the character still is valid, has all the required valid data, can still actually perform the movement, isn't destroyed in the game world, all of that fun stuff. Very simple, right? And if it's not the case, obviously return. Don't actually run this logic. And then we're going to just check to see if we were teleported, because the engine supports teleportation in multiplayer and whatnot out the bat. Quite nice. And then we can also imagine that if our movement mode is set to none, we obviously don't want to run anything when we're doing perform movement. The same thing goes for the mobility if it's set to static, remember in the engine, let's go ahead and grab whatever these are. 3 different things, right? Static, stationary, and movable. Obviously, if you're not movable, you shouldn't be able to move. So self-explanatory, right? And of course, whether or not, once again, they're simulating physics. Remember, physics, the actual engine physics, is different to the physics that we're trying to do here in the character movement component. And of course, if any of these conditions are true, we're going to basically want to stop anything, right? We don't want anything to occur. So first up, we're going to just check to see if the client's updating. We'll get more into what that means in the next episode, but basically this just means the client is currently replaying moves after server correction. And then bserver ignore root motion basically just says, okay, the server doesn't want you to use root motion. And this is most commonly used when you do something called a dual server move, when you're combining 2 moves together, because obviously you don't want to double tick something, right? Because if you go back to the code, we can see here that effectively, if these are fine and dandy, we're going to be ticking the character pose, basically just like getting the animation along and then clearing all root motion parameters. Because we do not want any root motion to occur in this particular update because of, we don't have movement, or we're static, or we're currently simulating physics. So therefore, clear everything and clear our accumulated forces as well while we're at it. Basically just says, yeah, get rid of all my root motion stuff, get all this kind of stuff. So long as you are not, replaying server moves, and as long as we're not ignoring root motion, then yes, move the character pose along and then just clear everything out the way. We don't really care about anything else at the moment. And then just return. But let's just say, everything's fine and dandy. This is more of just like a little check. Then we're going to move on. And this force floor check is actually quite nice. So basically it just says if something occurred, for example, like a teleportation or something along the way, you kind of want to know what's happening with your current floor, whether or not, you should land, whether or not, information regarding, for example, starting to slide off an object, or basically just forces an updated check to make sure that you can still stand on the thing you're standing on, or you're in the air still, things like that. Now we get to the really fun stuff. So, remember root motion, right? So basically, if any root motion stuff occurred, well, that since the last update, whatever the case is, you want to ensure that that particular information, that velocity information from the root motion, is added and factored into your physics simulation. So basically, this is what you get to see over here. Even there's a bunch of little debug things. You can see how the root motion works and all that kind of stuff. And also, this is a typical little thing. You always want to cache your old velocity, your old location. You'll often see that a lot throughout the engine, and also you probably do it yourself a lot, because that allows you to see your previous velocity, your new velocity, and then calculate your delta velocity. It's also quite common to get information from the last frame and compare it to the new frame to see also what changed, what's the delta, and that's important, for animation, all that kind of stuff. But that's just an example. Let's move on over here. Here we got something called a scoped update. So I'm going to give you my best explanation I can of how this works. I hope I'm getting all the facts right, but I'm pretty sure this is like a good little overview. So let's just go ahead and have a look, shall we? So if we were to go and have a look at, let's go into look at enable scope movement updates and go and check out the definition here. We can see that high-level movement updates will be wrapped in a movement scope that accumulates updates and defers a bulk of the work until the end. When enabled, touch and hit events will not be triggered until the end of multiple moves within an update, which can improve performance. This makes sense. If we were to go now into, or if you can see over here, improve performance of multiple move component calls. And if we actually see what this means, what the definition of this is, we can see here that allows for propagation of moves that may be deferred until the end of the outermost scope. Well, that just means, I'll do a bunch of these moves and then worry about something later, effectively, right? So in this case, it doesn't worry about updating the bounds, update transform, update physics volume, update child transform, all this kind of stuff, which means that after every single little move you do along the way within the scoped update, it won't be doing a huge amount of this sort of like checking for overlaps, checking for other little hits and whatnot along the way. So for an example for this, let's just scroll down a little bit, right? Let's quickly find one of those move component things we just spoke about. Yeah, move updated component. You're going to find 2 main functions, move updated component and safe move updated component. So what we're doing is basically we're going to be moving the component around a lot in this function. I mean, a lot of things can move it, right? I mean, the physics functions can move it, a whole bunch of other little things, and even this little part here can actually contribute to moving the updated component. And also, if you think about it, inside of the physics functions themselves, you get something called subticking, which means that they can tick multiple times per frame, potentially. So if you're doing this amount of sort of movement updates, obviously, deferring all the other stuff till after all of these movement little updates can save a fair chunk of performance. It's otherwise, can be pretty arbitrary, right? To sort of move it a little bit, update those things, move it a little bit, update those things, move it a little bit, update those things. So now we're just doing all the movements we need to do, and then just deal with all the other stuff after the movement update, which makes a lot more sense, right? Because these are micro adjustments. Think about how fast a computer is, right? When you're doing this movement every frame, you're moving like a little tiny bit that particular frame, and then it updates multiple times per second, obviously contribute all depending on what your frame rate is, right? So now you can imagine that adds up. So that's why you want to defer some things till after the movement update in this case, and that's why this scope function exists. But let's go back up to where we were so we can continue talking about the important stuff. Here's a little part here where you just cache your current velocity and your current location so that you can then perform the physics move and then see the delta afterwards. What changed? How did my velocity change? How did my location change? And that informs a lot of other little things, right? So, but moving on, apply accumulated forces is quite a nice little function. So if you ever applied an impulse to a character and wondering how that actually gets applied in the back end, here it is. So you can see you just constantly just adding, basically all that happens is that it just adds that impulse to the velocity. Now, velocity pops up a lot, right? You're seeing this recurring sort of theme. And if we actually, to stay on the topic of velocity for a second, if we scroll down a little ways here, you can see that all of the calculations to do with root motion and whatnot, they are also just straight up added to the velocity. And now you're wondering, okay, so you're just adding things to the velocity, what's going on over here? So you might begin to see little ways of hacking this component to make it easier on yourself to sort of change up how these different modes work. But we're going to cover that particular little hack in, I think, probably towards episode 3, where we do the blueprint only solution, and you're going to see some pretty cool stuff with how to hack this component and get its stuff working in multiplayer very easily. And a lot of that has to do with just hacking around with the variables, hacking around with velocity, things like that. You'll see what I mean when we get to that particular section. But for now, let's move on. Here's one of my favorite functions, particularly for multiplayer, because in a sense, like, I know scoped might be the wrong word to use here, but it's kind of like a scoped function. It's in a very nice little spot. Basically, update character state before movement. It's self-explanatory, right? Just do something before we perform the actual physics movement. In this case, it just does stuff with crouching and uncrouching. But it can be extended by you to do really cool stuff, because this is a virtual function in C++ that you can play around with. So that's nice to have these functions. That means you don't have to worry about rewriting this whole function if you just want to like sort of add a little bit of code into very specific places. And of course, you'd probably just want to do something before and after a movement update, and those are the only real spaces you really want. So boom, there's one of the fancy little functions for you to work around with. And of course over here, if you've ever worked with the character, you've probably done a launch before, or potentially you've done a launch before, and this is what actually happens. You kind of like requesting a launch in launch character, which applies at a pending launch velocity, and then in handle pending launch right here is where that actually occurs. You can see, so long as we actually have information, actually have launch velocity, it straight up just sets the velocity to that pending launch velocity, which, so of course, you can also change this behavior if you want launch to accumulate with your current velocity rather than just straight up just changing the velocity to this particular thing. You can change that here, stuff like that. I have also a nice little function to override. But if you're wondering where launch occurs, this is actually where launch occurs, in handle pending launch. And then after we've done all those things, we've now already gone ahead, right, and applied all of the various forces and impulses. We've applied our pending launches. Then we just want to clear all of that crap, right, and move on. Because you don't want this to be sitting there for the next tick. Because remember now, once you've consumed something, you want to make sure you clear it out, which is why we also clear the input velocities and all that kind of stuff, and also clear the root motion once it's been handled as well, stuff like that. You can see that little section here of root motion once again. But remember now, moving on to root motion for a little bit here, remember how we spoke about how the root motion comes from the animation, correct? And this is almost like another way of handling an input vector, as we mentioned, right? So effectively, you're just taking velocity from root motion and applying it on here. Easy enough, right? That's what all this here is. It's a whole lot of that code just to do that kind of stuff. And there's a little bit of extra code in here. For example, if you're locally controlled, you want to obviously store your current root motion information to be sent through to the server at the appropriate time. You can see that over here. It can be used when we've been networking code. So that's, remember, as mentioned a little bit previously, we're going to be doing this move locally and on the server. So obviously, when you've done something locally, you actually want to send it through to the server afterwards. That's what a lot of this code here says. So I'm going to speed up a little bit here just to get through the boring little bits so we can get to the meat and potatoes. Sure, I've done a lot of those comparisons lately. This is not a vegan tutorial, apparently. Anyway, So after you've basically consumed your input vectors, right, you've modified your velocity as much as you want to before the actual physics starts. That's when we get to the fun bit that we talk about right in the beginning, the start new physics. And bam, we're back to where we are with phys walking, phys nav walking, phys falling, and now you can see, depending on which movement mode you're in, we can now take that velocity information, can take, the acceleration, all that kind of stuff that we've already accumulated, grab the information from the root motion stuff that's moved us as well, and actually apply. Because if you imagine now, depending, no matter what you've done, let's say your character's here, very well drawn one, and you want to move forward. And let's say you've done a dash ability with a root motion animation. Obviously, you're going to be changing the velocity of the character, but along the way, you're going to want them to bash into this wall. You don't want them to go through the wall, right? Which is why it's important then for the root motion to be accumulated and applied so that the physics functions know what's going on, so that they can then basically change the end result based on the environment. And that's all we've ever done, right? Even with the normal input vector approach, if you add an input vector, you get your acceleration that applies to your velocity, and velocity is what drives these physics functions. They're checking to see what direction you're going in. What is it along the way? Can you jump over a little stone? Can you slide up a surface? All these little things, right? And that's all you're doing. So that's why velocity can be quite a cool little hacky thing to play around with. And like I said, we'll get into some fun stuff with that at some point. But for now, we'll just focus on these. So now, what actually constitutes a physics function? Let's go to one of the more complicated ones, the walking. Why is walking more complicated? Just because, you're on the ground, there's rocks and stuff to climb over, there's stairs, there's a whole bunch of things you want to worry about, potentially. And we're going to get into a little topic here that's, where is it now? Oh, here it is. Here. This remaining time stuff, right? You've actually right in the beginning, if we go back to the start physics function itself, you can see a delta time and iterations. What does this mean? Well, effectively, this component does something called subticking. And what this means is that, as mentioned, computers are pretty fast, right? So what this means is that if there's enough performance headway, you can run this physics function multiple times in that particular frame, which is pretty nice. It just allows for a higher fidelity simulation. But of course, if you want to change halfway through, let's say you have now moved off a cliff and are falling, like in this case here, you want to start new physics at the current time as well as how many iterations you have left to actually run this frame. I do believe standard is you can do maximum of 2 iterations, I think. I might be wrong. But basically, yeah. So that's all that means by subticking. And that's what I meant by subticking earlier when I spoke about the scoped movement. And now you can once again see why that's important to because you can imagine how many times in that one tick are you currently moving the component and doing all this little bit of maths and whatnot. So that's why you're trying to defer that stuff as well. So you can see why this component has so many lines of code now, right? It's just optimizations on top of optimizations on top of networking on top of that. So that's why it can be so daunting, but it's not too bad once you get into it and understand it. So that's why you'll see this recurring within the various physics functions. So you can get that extra little bit of fidelity along the way. Now, in the main body of the function, we're basically going to just do what we discussed previously with moving along the ground. Like, what exactly is going on? Obviously, you're moving along the ground. If you're checking for objects that you bump into, can I climb on top of that object? Can I go up a slope? What kind of angle is the slope? Does it fit within the maximum angle I can walk at? All these little things are being calculated here in this particular function. And we can kind of see that right here. So first off, let's check what the velocity says if you calculate your own velocity. And you can kind of see that basically it says, well, if you have acceleration, add that to the velocity, do a bunch of these other little checks to make sure everything's good and dandy. If you do not have any input, obviously there's no velocity. So if there's 0 velocity, obviously you want to start applying braking velocity. And in this case, let's go back a step or 2. You can see past in that infamous little thing, the friction, which remember we don't really use, at least like I don't really want to use it, and maybe you don't want to use it, so that's why we turned off friction. But you can see this is a reusable function for all the different physics functions, right? To calculate the velocity in a given situation. Because they're all very similar, remember. So we just pass through the current braking deceleration, which you'll see, if we're considering that we're in move walking, we'll use a particular kind of one for move walking. If we go back to the function, you can see there, yeah, if we have 0 acceleration or 0 requested acceleration, then obviously you want to slow down, start applying your braking velocity. and so on and so forth. You can just read through this and see how it all works, but it's pretty self-explanatory. And of course, once you've calculated your velocity, oops, back one, there you go. Now we can start saying, okay, well, if we've after we've applied our root motion to velocity, obviously this is once again quite self-explanatory. I mean, all you're doing is adding the root motion velocity to your velocity, and whatever the case is, simple enough, right? And that particular situation can push you over an edge. So now we need to make sure that if we're now falling all of a sudden, if root motion has pushed us into falling, we want to start new physics, because remember, we might have enough physics left to actually start the new physics mode, in which case you'll start falling for maybe one iteration left in the particular tick cycle, and then from the next tick onwards it'll keep in that movement mode until eventually you land, or whatever the case may be, and it'll swap back to this one. So you can see the movement modes in themselves can switch into other movement modes when they detect a particular change. Like in this case, you'd often change between falling and grounded, quite a bit of ground movement. That's important to keep in mind. And also from there, of course, we want to actually move along the floor with our new movement velocity. Now, moving along the floor is obviously where we do a whole bunch of stuff. First of all, we actually safe move updated component will actually sweep. That's the big difference between move updated component and safe move. So in this case, you can actually assign a hit value. And of course, if you bump into something, it'll actually say, oh hey, you're starting to penetrate a surface. Therefore, calculate some stuff, see what you can do. Can I slide along the surface? For example, if I run to a wall, but at a certain angle, which means a certain amount of my velocity can actually move along the wall, you'll slide along that wall instead of just stopping flat in your tracks, which is what you'd want to happen. Now we can actually see that in game as well, if we can just start it up over here. If I hit back into a wall, because I have just enough velocity in a certain direction, I'll slide along the surface of the wall. Pretty self-explanatory. Also allows you to slide up and down surfaces. But of course, when you're grounded, you won't slide up surfaces. Like if I was trying to get velocity up that way, that's not going to work. But you can slide side to side. But if I was flying, then I would obviously slide up the surface if I was giving enough velocity in that direction. If enough of the component of my velocity was in that direction. So that's the cool thing about that function, right? That's quite nice. If we move along, we can also see we start doing stuff about the can step up. With that particular hit, can we step up over a rock? Can we do this? Can we do that? Once again, you can slide along surfaces, all the kind of stuff. So yeah, it basically just self-explanatory, right? The whole thing is just revolving around this little function over here. Just checking to see, what have I bumped into? Can I climb on top of it? Can I slide up and down stuff? What proponent or component of my velocity is in a certain direction? Can I hit a wall and then slide along it without causing too much trouble? All that kind of stuff. And that's what you'll find with most of these, actually. Like if you were to go to flying, as mentioned, it won't have the ground constraints of walking, but it has very, very, very similar functionality to walking. It'll still do little step-up checks, it'll still allow you to slide along surfaces, all that kind of stuff. And now back on the main page again, you can kind of see that if we've entered falling, obviously you want to start in physics. If we've just started swimming, we've just entered, for example, a swimming volume, which you can just drag out to the level and set as a swimming volume. Then, of course, start swimming. All these kind of things. And, of course, one very important part as well is finding your current floor. Like, is the floor you're walking on currently moving? Is it your new movement base? If it moves, do you move with it? Stuff like that. Is it valid? Am I walking on the surface of an angle that is too high all of a sudden? All these kind of things start happening here. Checking for ledges, seeing if I've just walked off an edge. There's also a prevention. There's a system built into the character movement component that if you tick the boolean on, it'll prevent you from walking off of any objects, which is quite nice. It can be quite useful if you're creating a game where you don't want the player to actually fall off of objects, fall off of surfaces. That's built in already in the character movement component. Could be quite useful for you. That's what you see here in this can walk off ledges section. Well, what else? Basically, that's all you really need to worry about, because you can see now the rest of it is if you're handling walking off ledges, checking to see the current floor stuff, checking to see if suddenly you're swimming, changing movement modes if you are. You can see it's just a whole bunch of that just repeated over and over again, and that's the end. That's all there is to it. And if you go through all the other various start new physics modes, if we look for that function again, and you'll see like flying, for example, very, very, very similar to phys walking. Once again, using that little function for calc velocity. And of course, you're getting the max braking consideration that fits with flying. And of course, once again, you're just applying your root motion to velocity like we did in walking. You're safe moving the updated component, you're checking for the hit, you're seeing if you can step up, you're checking if you should slide along the surface. You see, very simple. It's actually a very small function, like lots more than walking, because walking has a lot of constraints, right? You don't want the player to move upwards, and also the player can move around and do little things on the ground that aren't really impacted too much by flying. So that's why it's quite a sizable, more like a slightly larger function. Other little ones, of course, is like important ones is falling, but you can just look through all these different physics modes and figure out how things work. But we've basically covered all the important stuff, so well done. Like, those are the basics. In the next episode, we're going to be going through the major networking stuff, how to get your code to actually be properly network predicted, a little bit in the beginning where we discuss how the networking works, why it's been done that way for so long, and how to make life easier for yourself when you do that. And then episode 3, we're going to probably start getting into that blueprint only solution that we discussed, and I'll show you some really cool little hacks and things you can do there to make your life easier for creating multiplayer modes, or multiplayer network movement code inside of blueprints entirely, which is going to be pretty cool. I think stick around for that as well. But as always, I highly recommend going through the episode 2, just figuring out where things are, why things happen as they do, and that'll really help you a lot in your development journey, even if you're trying to just stick to blueprints as much as possible. Trust me, it's worthwhile going through the C++ stuff. And of course, if you're here for the C++ stuff, episode 2 is going to be your baby, probably. You're going to love it. I'm going to go through all the different things you need, basically how the old way worked, how the new way works, and we're just going to go through the whole damn thing. So, onwards to episode 2. Farewell.